Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. Before we proceed, I kind of like to request our members to subscribe, engage us in the comment section, and also ring that notification bell to be getting updates on various discussions we do in mathematics and sciences. Now, in our discussion today, I'm going to look at a concept in magnetism, and this is going to be basically emphasizing on the concept of electric currents and the magnetic field. Now, in this particular discussion, we are going to explore the relationship between the two, and of course, that's going to be, relying on the works of scientists, particularly two scientists who came up with an idea of finding the relationship between the two, and those are the works of Hans Christian Ørsted and, of course, a French physicist by the name Andre Marie Ampere. Now, we have come across these specific names perhaps in some of our illustration for dimensions in terms of units, like the amperes, which we measure the current. Of course, these ones have been named in this honor. So in this case, I'm basically going to be giving these specific names. Now, in case we come across them, of course, we're going to come across some of the dimensions being given in terms of those specific names as I've mentioned. So in this case, we are going to have this as well, a French scientists. Now, the two came up with ways of trying to define the relationship between electric currents and magnetic fields. Now, for the first one, of course, this is exploring the relationship between the two. And for the second one, Andre Marie Ampere gave us a way in which we can predict the direction of the car, of course, this specific magnetic field, insofar as this specific relationship is concerned. Now, Hans realized that basically an electric current is going to produce a magnetic field, and therefore, as I have said, that this is going to assist us explore the relationship between the two. So the electric current produced magnetic field. And in this case, we're going to see that basically we can give this particular relationship in terms of this specific symbol illustration. So suppose we have a conductor which is carrying a current in that specific direction, then we're going to see that there is a relationship we can use to define this one, or rather I can just use this one for the sake of a subsequent demonstration. So if we have an electric carrying a conductor, or a conductor which is going to be carrying some kind of current in this specific direction, we can find the relationship between this specific conductor and of course the influence of what we refer to as magnetic field, which it's going to be creating around its surface. Now, in this particular case, we're going to see that we can as well explore the direction, or find the direction of this specific magnetic field. But for the case of this electric carrying current having the effect of having a magnetic field around it, and therefore this work was done and discovered by the work of Hans Christian Ørsted. And of course, the subsequent work of determining which direction this specific magnetic field is going to be aligning with, it was done by this, or was explored by this French physicist by the name Andre Marie Ampere. Now, in this case, I'm going to use the demonstration which I've given on my top right side of the board. And that is going to assist me in trying to find the relationship as it was done by this specific scientist of Hans Christian Ørsted. Now, in this case, this is going to be in terms of a simple circuit. So we're going to have this switch, a rheostat, and a source of electromotive force for low voltage but high current source. And then we're going to have this, what we refer to as a plotting canvas, which are going to be a set of two given as such. Now, in this case, we're going to see that whenever we're going to close this specific circuit, the current is going to flow in this specific, of course, components which have been given as such. But in this particular case, we're going to see that if we bring a plotting canvas and place it above this current carrying conductor, we're going to have a specific deflection. And if we bring this specific plotting canvas as well and place it below this current carrying conductor, we're going to have another deflection, of course, which is going to be appearing in the opposite direction. Now, in this particular case, this arose the curiosity of Andre Marie Ampere, and therefore he came up with what we refer to as Ampere's swimming rule. Ampere's swimming rule, whereby he used the aspect of swimming in trying to define or rather trying to, of course, define the direction of the current, which or the direction of this magnetic field as it's going to be seen around this current carrying conductor. Now I'm going to use this particular illustration so that we can just have an understanding of the deeper details of this specific experiment. Now in this case, if we have a conductor that is of course carrying current in that specific direction. Now Ampere's swimming rules states that if a person is swimming along this direction of current given as such, and if he's facing, of course, this specific plotting compass which has been given in terms of this specific of course symbol, we're going to see that if he's facing this plotting compass, if he's swimming in that direction, of course he's facing this plotting compass, and then we're going to see that his left side, or the person's left side is going to, left hand is going to be facing the pointer. So the left hand, if the person is swimming, of course, in the direction of this specific current and facing this plotting compass, then the left hand of this specific person is going to be facing at the pointer or the north pole of this specific plotting compass. Therefore, that's going to be one of the ways in which we can identify the direction in which this particular, of course, compass is going to point. But if this one is placed below this current carrying conductor, and if the person is swimming in the direction of this specific current still, we're going to see that the person's left hand side is going to be facing this specific direction, of course, and which is going to be the north part of this plotting compass. Now, in an essence, Ampere's swimming rule is going to give us a clue on how we can identify the direction of this specific current. And in addition to that one, we're going to use what we refer to as the direction of this magnetic field can be determined using what we refer to as the right hand rule. So we're going to have the second one as the right hand rule. In this case, the right hand rule is going to be illustrated using this specific aspect which I've given for P, whereby if you try to grab a current carrying conductor using your right hand shown as such, we're going to see that the thumb is going to point in the direction of the electric current, which of course is going to be in this specific direction. I hope my demonstration is going to be elaborate, but we're going to see that the direction of the the direction of the fingers we point in the direction of the magnetic field being given as such. So we're going to have this one pointing in this specific direction, which is going to be the direction of the magnetic field. So in an essence, if this particular conductor was facing towards us out of the board, then we're going to expect this specific, of course, current carrying conductor to be the clockwise direction. But if this specific, of course, conductor is facing away from us, we're going to expect the magnetic field to be facing in that clockwise direction. So the two are going to assist us in trying to identify the direction in which this current is going to flow, and therefore that's going to give us a clue on the relationship between the electric field or the electric currents which I've given in terms of I, and the magnetic field which we have of course been using this specific